Hey there, Calc 2 folks, back here with what I hope is my last, I do think it's my last video here, covering Test 3 material where we are looking at sequences, series, and then taking that up into Chapter 11 here and building towards this idea of Taylor series, right? Where, if you recall, what's gotten us here to the idea of Taylor series is this idea of using a polynomial to begin approximating the value of a transcendental, right? To try to think about this value of a transcendental function near values of that transcendental, right? That we do happen to know. And we had developed this idea of a Taylor polynomial and its use in approximations, folks, right? And when you develop a Taylor polynomial of several degrees, right, that really does become a representative of that function that we are trying to, in a sense, approximate, that transcendental function that we're trying to approximate. Very close to those values where we say that we're centered at in that Taylor polynomial. Well, we're going to continue that idea today by going to the infinite degree with those Taylor polynomials. If we consider a Taylor polynomial where that summation happens to the nth degree where n heads off to infinity, we do have the case for what's known as a Taylor series. And as we're going to see in the definition of a Taylor series is really just a power series, right? It is this case for a power series, right? So, as noted at the beginning of the notes on power series, a Taylor series is really just a power series formed when the summation represented by a Taylor polynomial becomes an infinite series, right? And we see that developing down here. You see a definition that starts off very similar to that of a Taylor polynomial, an nth degree Taylor polynomial, but instead of having an upper bound on that summation that is indicated by the degree of the Taylor polynomial, we consider having that value of n be represented by infinity. In a sense, we have this summation that continues off towards infinity, right? Where in that summation, again, if you recall back to Taylor polynomials, we are taking this quantity, right, given by the kth derivative of f evaluated at our center of a and dividing it by k factorial, and multiplying it by this quantity x minus a being the center of our series, x being the variable inside this infinitely long polynomial, this Taylor polynomial, and k being the power on that quantity, right? Again, representing this index, right? What we note here for a Taylor series, it does assume that form of a power series. We do have this quantity given here, which represents that coefficient with respect to k back in a power series, that value c sub k, times this quantity given by x minus a raised to the kth power. All right? Together, they form a power series that is specifically known as a Taylor series. A Taylor series for a function we call y equals f of x, f typically being some transcendental function centered at some value of that function that we are aware of, that we don't have to spend a lot of time thinking about its transcendental value. All right? We might consider an example, right? Consider again the Taylor series here. And I think we saw this case back for Taylor polynomials, where we develop now a Taylor series for the function f of x equals e to the x, centered at x equal to 0. All right? In this definition above, function f is going to be replaced by, be played by the role of e to the x. A, the center in our series, is going to be played by the role of 0. Right? And we are going to form this infinitely long summation for the kth derivatives of f evaluated at a divided by k factorial times this quantity x minus a raised to the kth power. Right? In this case, for function f of x equals e to the x, we get a nice result for the derivatives of that function. F prime is equal to e to the x, f double prime is equal to e to the x, f triple prime is equal to e to the x, and so forth. The derivatives of the e to the x function, right, the natural exponential function, are always the natural exponential function, right? They are they are quick derivative results, right? Very fundamental results, right? Where if we now consider those values at our center, right, at that center of x equal to 0, right, f of 0 would be 1 in value, f prime would be 1 in value, f double prime would be 1 in value, right, and f triple prime at that value of 0 would be equal to 1 in value, and so forth. So then if we think about the Taylor series, right, the Taylor series we defined above here can now be defined in this manner. Again, the value of a is 0, so x minus 0 is just x raised to this kth power. All of our derivatives evaluated at our value of a, right, always will result in the value of 1, right? So down here, f kth derivative at a will always be 1 in this pattern. So we replace that with 1, and we're left with just 1 over k factorial as our coefficient c sub k, times this quantity x minus a raised to the kth power, or here x minus 0, or just x raised to the kth power. Where here, our Taylor series, in this case, forms this specific power series. Right? And how do we explore the power series? How do we look at its convergence as we consider its interval of convergence? We consider what are the potential values for x that might cause this series to converge. And we can seek out those values. And the way we do that is with the ratio test. Where in the ratio test, this argument is going to become a sub k. And we are going to compare hold on here. Not erase that value. But this argument here is going to become a sub k, right? And we're going to want to consider what is a sub k plus 1, right? Replacing these values of k with k plus 1, and then consider how would that ratio of a sub k plus 1 to a sub k simplify. If we arrange that here, this would be the value of a sub k plus 1 times the reciprocal of a sub k, where we will see the k factorials cancel, we will see the a sub k's cancel, or a of k's cancel, a to the kth powers cancel, where we'll be left with just this factor of x in the numerator over this factor of k plus 1 in our denominator. All right? That will be the ratio of a sub k plus 1 over a sub k that we see used in the ratio test. Where if we now take note on what's going to be the value of the ratio test, r, and if we think about the value of r, that was a heck of a split there for the and r then, right, is going to equal this value here. It's going to be the limit as k heads to infinity for the absolute value of this ratio, or the absolute value of x over k plus 1. We see that given here, right? And if we take note, the absolute value symbols will only apply to the x. Since k will always be greater than 0, starting or greater than or equal to 0, starting at 0 and heading off to infinity, they aren't going to be needed down here in the denominator. They will only be needed up here in the numerator for x. And then furthermore, if we think about this being a limit with respect to k, the value of x is a constant, and its absolute value can be factored out of the limit as a constant multiple of the limit. And if we see that setup, that will produce this setup, right? That absolute value of x will factor out, and the absolute value applied to what remains won't be necessary, so we'll just be left with what remains, 1 over k plus 1, where we now evaluate the limit of that as k heads to infinity. And the fundamental rules of limits say, well, as that k heads to infinity for this ratio, well, that heads to 0. So what we have is the absolute value of x times 0, which is just 0 in value. The ratio test performed on this Taylor series says that the result of the test will always equal 0. That value of r will always be equal to 0, regardless of the value of x in the power series. Right? So, what does that tell us about the interval of convergence? All right? Well, when this happens, right, that ends up implying, right, since r is equal to 0 is less than 1 for all values of x, and when r is less than 1 implies convergence in the ratio test, what we can conclude is this power series, or this Taylor series, must converge for all values of x in this interval of convergence from negative to positive infinity. There are no boundaries on our values of x that will cause the test to produce a divergent result. Regardless of our value of x, r will always equal 0, which produces this convergence result in the test. Right? So in this case of the Taylor series, it is convergent everywhere. Right? It is convergent everywhere. Right? Now, again, we did that just by performing, as we had done back in the case for power series. This is just a power series, right? Where we've set that up by using what we call a Taylor series calculation, right? Where with any power series, we begin that test for convergence and intervals of convergence using the ratio test, right? And in this case, as we've seen in other power series, we've obtained this interval of convergence that is everywhere from negative to positive infinity. Right? Now, all this tells me is that I converge everywhere. What it doesn't necessarily tell me is where I converge to. Right? What has been suggested in terms of where we converge to, right? And what I take note on here, as for the value a Taylor series converges, upon, right, the following theorem takes note on this value. Right? This theorem states the Taylor series x, right, for our function y equals f of x centered at x equal to a, converges to f of x if and only if, right, I should really say converges to f of x centered at x equal to a, right? If and only if the limit for what would be the remainder in what is essentially the difference between, right, the polynomial function and the Taylor polynomial given by t sub n of x, right, this remainder r sub n of x heads to 0 as n heads off to infinity, right? If we think about the Taylor series up through the nth term, you do have an nth degree Taylor polynomial, where when you take its difference between that and the actual function we're approximating, centered at x equal to a, right, the remainder is going to be the difference between the function and that nth degree Taylor polynomial. And that functional description given by r sub n of x, if as n heads to infinity in it heads to 0, right? Which we note that value of r sub n of x is equal to this here, right? Right? Given by this here for some value of c between x and a, well, x and a in value, right, actually converges to the value f of x, right? I don't think I need that here. Actually, this is what it's pointing to, right? Is that y equals f of x, right? the Taylor series for y equals f of x centered at x of a actually can be said to be equal to f of x, is what we're saying here, if the limit of this remainder is equal to 0. Right? If you can show the limit of the remainder where the nth degree Taylor polynomial is used to approximate f of x heads to 0 as n heads to infinity, then what we're able to say is that our Taylor series, right, must converge on the function we're approximating, right? Must converge on that function we're approximating in its interval of convergence. Converge to f of x in the interval of convergence for t of x, right? If and only if, man, I'm way out of bounds here, converges to, what is going on with this? Yeah, let's get it in there like that. Something going on with the word editor there, right? To f of x in the interval of convergence for t of x, if and only if this is true about our limit. I think that's what makes it a little clearer as a theorem. All right? As how we're going to then calculate r sub n of x, this was actually given back in what's called Taylor's theorem back in 11.1. I didn't spend a lot of time on Taylor's theorem because we come back to it here. R sub n of x can actually be approximated this way. What remains as a remainder between f of x and t sub n of x is going to be this quantity here, right? Where you'll notice this quantity here is just the nth plus 1 term given by the Taylor polynomial, right? If we were to go 1 degree further into the Taylor polynomial, there would be one more term, right? And r sub n of x, the remainder, would be equivalent to that term, right? Would be equivalent to that term at some value of c between x in r sub n of x and a, where this Taylor polynomial is centered, right? Well, what does that all mean if we look at that in practical application, right? We might consider t of x equal to this, right? The previous case for f of x equal to x near x equal to 0, right? The above theorem ends up telling us, in a sense, that this Taylor polynomial t of x is essentially the exponential function for all values of x in the interval of convergence for that Taylor polynomial, or for that Taylor series t, right? T of x, right? If and only if the remainder for the nth degree Taylor polynomial in this case heads to 0 as n heads to infinity, right? Where, since f of n plus 1 of x would be simply equal to e to the x in this case, since all derivatives of function f in this case will be equal to e to the x, we're able to then say that r sub n of x, right, this value given here back in our theorem, must be equal to f at c, so e to the x at c, which would be e to the c, times x minus a raised to the nth plus 1 power divided by n plus 1 factorial, which I've brought here into its own factor. Must be equal to essentially e to the c times this quantity, right? Where we might take note, if we think about then the limit as n heads to infinity in that remainder, right? That value e to the c, first of all, is a constant multiple, and it would be brought out in front. And you would be left with the limit of this quantity here, where the limit of this quantity here is simply 0. And how we know that is by just noting the limit of the growth rates here, folks. This numerator grows slower than the denominator in terms of their growth rates. So if this numerator grows slower than the denominator, this overall ratio will actually head to 0 as n heads to infinity. So using some growth rates here, we can show this heads to 0, or that in a sense the limit as n heads to infinity for this remainder must be equal to 0. All right? So what does that tell us about our Taylor series? Well, that Taylor series then must be equal to e of x, right, for all values of x in that interval from negative to positive infinity, right? Therefore, we can conclude that when we think about that transcendental function e to the x, that transcendental function e to the x is really nothing more than this infinitely long summation. Right? It really is nothing different from, right? If we started to spell out this summation, that would be 1 plus 1/2 times x squared plus 1/6 times x cubed. Do I have that? Oh, back up, I'm missing a term. Plus x, plus 1/2 x squared, plus 1/6 x cubed, plus 1/24 x to the 4th, plus 1/120th x to the 5th. Let me fix this. X to the 5th, and so forth. All right. What this above result tells us about the remainder is that e to the x, that transcendental function f of x, equal to e to the x, it must be equal to this infinitely long polynomial. Right? For all values of x in its interval of convergence. And notice here, it converges everywhere. So in a sense, e to the x must be equal to this infinitely long polynomial for every single possible value of x. Right? And folks, this is what your calculator relies upon when you ask it to calculate different values of powers of e. Right? That e to the x function on your calculator, what it has stored inside of it essentially is just a polynomial description that goes out to several degrees. It basically stores here an nth degree Taylor polynomial based upon, right, this description of it out to several degrees. And by several degrees, I mean it could be out to the 10th or 20th or even the 100th degree, where you're going to get levels of precision in your decimal here for the approximations of e to the x that your calculator spits out as a decimal that will be accurate out to what could be to the nearest millionth or 10 millionth or billionth or trillionth, right? Just depending upon how much of this infinitely long Taylor polynomial your calculator happens to be programmed to use. Right? And similarly then, if you wanted to calculate things like derivatives of e to the x, you could use your derivative rules like e to the x, but you could also use portions of this polynomial. And likely that's what a lot of calculator programs do. Or if you're considering finding the integral of e to the x over boundaries of x, right, you could rely on a portion of this infinitely long Taylor polynomial, right? Where, again, if you think back, polynomial calculations are rather fundamental, well, I should say all involve just fundamental arithmetic, right? Fundamental arithmetic that our calculator systems are built upon: addition, subtraction, multiplication, and division. That's all that's happening here, is addition, subtraction, multiplication, and division in these power series. All right? So here we have a way of thinking about this transcendental in terms of just addition, subtraction, multiplication, and division. All right? Which is pretty interesting if you if you've caught on and you're thinking about this, folks. All right? Let's look at another example. All right? Let's consider the sine x. There's a transcendental function. We know its values for a couple of key locations around our unit circle, right? Typically, we know it for values that output what? Square root of 2 over 2, or 1/2, or root 3 over 2, right? Or 0 or 1 in value, but we don't really know it for any real other angle measurements or values of x outside of a few common locations, right? So let's see, let's think about maybe developing a polynomial approximation of this function centered at x equal to 0, right? If we do that, all right, we will note that, first of all, for f of x equal to the sine x, the first derivative of f would be cosine, the second derivative would be negative sine, the third derivative would be negative cosine, and the fourth derivative would be sine. Where then the fifth derivative, the sixth, the seventh, and the eighth would all cycle back through these first four results again, and that would continue on indefinitely, right, and so forth. So if I think about evaluating these results at x equal to 0, we will see the values of the derivative cycle from 0 to 1 to 0 to negative 1 to 0 to 1 to 0 to negative 1 to 0 to 1 to 0 to negative 1, and so forth. Such that if I actually think about the Taylor series, if I spend a moment denoting what t of x might resemble, t of x built term by term would start to look like this here, where you'll notice there is a pattern forming. Every even power of x minus 0 raised to the second power will actually zero away, and you'll be left with these odd terms of the polynomial, right? And really, I should say here, plus, this goes on ... forever. Where, right, if we consider continuing that out and dropping out those 0 terms, we actually have this series here. This infinitely long series that does follow a pattern. The next one in the pattern here would be 1 over 9 factorial times an x raised to the 9th power, right? There's a pattern there. And the next one in the pattern would be negative 1 over 11 factorial times x raised to the 11th power, right? There is a pattern that is definitively happening here, right, as we progress from term to term in this Taylor series. If we think about defining that pattern, right, we might define that pattern this way, right? For t of x equal to the pattern given above, we could say that that's the summation from k equals 0 to infinity for what is negative 1 raised to the kth power over what is now 2 times k plus 1 factorial times this quantity of x raised to the 2k plus 1 power. What we do notice is we have an alternating series, so that is handled by having this negative 1 raised to the kth power. And how we make the factorials go, exhibit just the odd values relative to k, well, we use the quantity 2k plus 1. From 0 up to infinity, 2k plus 1 will produce only odd numbers, 1, 3, 5, 7, 9, and so forth. Right? And we can use that same value, 2k plus 1, on our powers of x. Right? So what we've formed here is another power series, folks. Right? This is a power series. Right? I will tell you, it's a bit of a hybrid series, but nonetheless, you'll notice here, you'll go, well, that's not a power of just k. You could write it as a power of k by making some adjustments within the series, folks. We're not going to make those adjustments. We're going to go ahead and just approach this as a bit more of a hybrid power series. All right, it's a bit more of an advanced power series, we might say. All right. Note in this case, t of x is described by this power series, advanced power series, where we can apply the ratio test. If we apply the ratio to that test to this, folks, it does get a little heavier, but it follows the same way, right? If we think about the ratio of a sub k plus 1 over a sub k, and more so the absolute value of all that, first things first is that absolute value symbol is going to kick out this negative 1 raised to the kth. It's going to eliminate that in a sense. It's going to cancel with that statement. So you won't see that given down below here. And in fact, the only thing it's going to apply itself to is the statement of x. So you do see that used here, and you do see that used here. Now, if we replace all our all our k values with k plus 1, these quantities of 2 to the k plus 1 power will become 2 times the quantity k plus 1 plus 1, which if we simplify all those statements, all right, you'll see that's what happens in my next line here. They will turn into 2 to the k plus 3 power, or 2k plus 3 factorial. That 2 will distribute 2k plus 2, and then we'll just add on this 1. Right? This will be 2k plus 1 factorial. This will be x to the 2k plus 1. All right? And the absolute values will still be affecting these values of x, but the values of k will have them dropped away, right? The negative 1 to the kth power eliminated by those absolute values, right? In a sense, canceled by it, right? Where if we now think about how we could expand the absolute value of x to the 2k plus 3, well, really that is just x squared times x to the 2k plus 1 power, right? If we were to take these same bases, powers of the same base, and combine them, we would just add the powers. We would be adding this 2 to the plus 1, and that would be making the plus 3. Well, I can turn the plus 3 into plus 2 and plus 1, where the plus 2 can then be broken out as this x squared quantity, leaving behind the x to the 2k plus 1. And that's kind of helpful, because that'll cancel with this x to the 2k plus 1. A similar thing can be done with these factorials. Right? Well, not quite similarly. 2k plus 3 factorial is really just 2k plus 3 times one value less than it, which would be 2k plus 2, times one value less than that, which would be 2k plus 1. And that would continue in pattern, right, all the way on down, where you could stop at 2k plus 1 and just say that that pattern continues using the factorial symbol. So 2k plus 3 factorial is really just 2k plus 3 times 2k plus 2 times 2k plus 1 factorial, where that's convenient to write because that will now cancel with this 2k plus 1 factorial. Right? And if those quantities cancel away as indicated, we will be left with this statement here. All right? That will be the argument that's going to go into the quantity we see in our ratio test. Right? If we then think about the ratio test for the limit applied to this quantity given here, right? Oh, and you'll notice in this quantity here, I also dropped the absolute value from this statement. The absolute value is not needed around an x squared because an x squared is always positive. So that does disappear here also, right? So we now just have the limit as k heads to infinity for this statement here, where the x squared relative to k is a constant multiple. It brings itself out in front, and we're really just left with the limit of this statement in terms of k. And if you note, that is another rational form whose k, as k heads to infinity, the denominator will grow without bound, but when dividing it by 1, or dividing 1 by it, heads to the value of 0. So really what we have here is x squared times 0, which is just 0. Notice when we apply the ratio test here, r will equal 0 regardless of our value of x. Or what does that tell us? Well, that tells us that this Taylor series, t of x, right, must be convergent for all values of x in the interval from negative infinity to positive infinity, right? As for what does it converge to over that interval, we can note, if we think about the value of r sub n in this case, what would be the value of f at n plus 1, right, evaluated at c, times x to the n plus 1 over n plus 1 factorial. Any n plus 1th derivative of the sine of x is either going to be plus or minus sine x or plus or minus cosine x. Where if we think about that at any value of a constant c, plus or minus sine x and plus or minus cosine x will always be a number between negative 1 and 1 in value. So the quantity that's out in front here for r sub n of x will essentially always be some constant value between negative 1 and 1 in value. All right? Or if we think about the actual value of f of n plus 1 evaluated at c, it will always be less than or equal to 1. I should really say in its absolute value. Yeah, right? Further implying then that this value of r sub n this value of f, let's see here. Okay, implying then if I just think about this value alone, right, times this quantity, it will always be less than or equal to 1 because its absolute value will always be less than 1, right, times this quantity here, which is just this value here, or in other words, well, or we can point out, and since the limit as n heads to infinity for this statement here equals 0, again from just an analysis of the growth rates from the numerator and denominator, what we can conclude is since r sub n is less than or equal to this quantity, right? R sub n is less than or equal to this quantity seen here on the far right-hand side. The limit as r sub n must also equal 0 in this statement, right? Implying then, if we think about the sine of x, that transcendental value in a lot of cases, right? The sine of x must be given by this infinitely long Taylor polynomial, right? The sine of x must be able to be set equal to this infinitely long Taylor polynomial for all values of x from negative infinity to positive infinity. And if we go back and actually take note of what that looked like, right, that was this polynomial function right here. Right? If I bring that down here, oop, hold on, how am I going to capture that? Capture it that way, bring that down here, plug it right in there. Dot, 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 right? So the sine of x must now be just said to be equal to this infinitely long polynomial, right? And it equals that for every single possible value of x that we can have in the sine function, right? For every single possible value of x we can have in a sine function, we can find its value by using this infinitely long polynomial with respect to x. Now, certainly we can't evaluate an infinitely long polynomial at every single value of x in this interval, right? But we could do is approximate the sine x to a very high degree of decimal, right? To a very high precision of decimal places, right? By carrying this polynomial out to several degrees, and by several degrees, we could go out to the 10th or the 100th or the 1,000th degree. Some computers nowadays can approximate that out to a very large degree, right? And that high degree polynomial description here, right, is going to give a description of the sine of x to several significant digits, right? And that's what our calculators are doing. When we go to plug in the sine of the number 1 into our calculator is really just plugging 1 into this polynomial out to several degrees, right? And it's calculating this just sum, difference, multiplication, and division of values, right? And giving that approximation back as the approximation for the sine of what we were interested in with respect to x. And we know, based upon Taylor's series, that this is going to be true for every single value of x, right? Folks, that is the end of my lectures here over sequences series and specifically now Taylor's series. And hopefully you've seen what we've been preparing for is getting to this state. In terms of the grander big picture, keep in mind what we're looking at is calculus. And part of calculus is the study of limits, and we're certainly have been using limits here in our study. But it's also using the study of limits to help us calculate values. Help us calculate values that are rather complex in their calculation, right? Something like, how do I calculate the sine for values of x that are not just those key locations on a unit circle? Well, calculus has given us a method to do that with this polynomial approximation, right? How do I calculate, go back up to our previous example, how do I calculate values for the natural exponential function e to the x, right, if I didn't have a calculator, right? Certainly I know its value at 0, that's 1, but how do I use that as well as my understanding of calculus to calculate this value for any other value of x? How do I calculate it for any value of x from negative to positive infinity? Well, the way we do that is with this infinitely long polynomial, folks, right? And really we don't get an exact value up to the infinite degree, right? If I needed to know e squared, well, e squared is just e squared. It's some infinitely long decimal value. And how do we begin approximating that infinitely long decimal value? We can use portions of this infinitely long polynomial function, right? And that's what calculus is having us study here, is how do we calculate these complex values? Here, the complex values of e, these transcendental values of e. Well, we can use this polynomial, right? This Taylor series as a description, right? So, folks, that does end it. What we're going to come back to, you have your test, right? Your test is out there. You're working on that, hopefully. I'll be in Blackboard Collaborate all week for questions over that. That's due in about a week's time. Then we'll be back to Chapter 12. So you're going to start, we're going to be changing gears again and looking at representing position in space and talking about the position in space beyond the rectangular ways of doing things. We're going to look at parametric descriptions. We're going to look at polar descriptions and see that going on in Chapter 12. And then we're going to wrap up the semester in Chapter 13, introducing ourselves to the beginnings of vectors and vector operations and vector descriptions of location. So that is all how we're going to end here, folks. And we're about halfway there with the notes. And in fact, we're a little over halfway with the notes, I would say. What we have left is really about 8 more sections to talk about. 8 to 10 more sections to talk about here, folks. 4 sections in chapter 12, and then I think there are 6 in chapter 13 that we need to look at. But I'll be back with those videos, and I hope you're hanging in there. Again, you know where to find me, and I'll see you next time, folks.